Okay, so at this point in time, we've made this connection between average velocity and instantaneous velocity, and we've seen them both in the physical sense of a ball being thrown up in the air, the average velocity between two time intervals, and then what's the instantaneous velocity of the ball at any given time. But we've also seen this from a geometric point of view by looking at the slope of the line. Now, we're going to get into this concept of instantaneous velocity and how to determine an instantaneous velocity using what we call limits. That's going to come on a little bit later in the course. But I think the question that we need to ask ourselves is, what is the instantaneous velocity at some time interval, t equals a, of this moving object that we have a position function for? How do we calculate the instantaneous velocity of that object? And what we're going to be doing is we're going to be computing a series of average velocities on some interval from A to B, but we're going to let that interval get smaller and smaller and smaller and smaller. And as that interval gets microscopically small, we're going to start seeing that this average velocity is really taking on the behavior of an instantaneous velocity. So we're going to introduce a couple new variables here. We're going to introduce this variable h. So we have this interval from A to B, but now we're going to say that B here, B is equal to A plus h. So if I start at A and I want to move out this way, I'm going to move out h units. So now this interval right here, which is B, is really A plus h units, A plus h. Okay, now this average velocity now from A to A plus h, which used to be A to B, but now we're going to call it A to A plus h, is the same average velocity function that we've been studying. It's going to be S of A plus h minus S of A divided by h. Now this might get a little confusing down here. You go, well, where did the h come from? Well, the h in the denominator, if you remember, the denominator is the A plus h minus A. And if we take A plus h minus A, that just gives us h. So that's where that comes from. Now, keep in mind here that h is going to be a small positive real number, but also h can be a negative number. It is going to be small, though, because if we're talking about instantaneous velocity, we want that h value to get smaller and smaller and smaller and smaller, and we want to get microscopically small. So it is going to be a relatively small number, but it can be positive or negative. If h is negative, and we'll talk about this more later, but I want to bring this point up now. If h is less than 0 or h is negative, then the average velocity from A to A plus h is really the average velocity from A plus h to A, because h is now a negative number. Don't get too confused by that. We'll talk more about it in this upcoming example. Okay, so here is the example, and don't be offended that I read this out loud to you. We have a falling ball. The position function of the ball is S of t equals 16 minus 16t squared. S is going to be measured in feet. T is going to be measured in seconds. What we want to do is find an expression for the average velocity of the ball on a time interval from 0.5 seconds to 0.5 plus h. But the restriction is h can only be between negative 0.5 and 0.5, and h cannot equal 0. We're going to use the expression that we get to compute the average velocity on the time interval from 0.5 to 0.75 and from 0.4 to 0.5. We're also going to make a conjecture. We're going to have a hunch about the instantaneous velocity at t equals 0.5. Now, we're going to do the solution in a separate video, but there are 3 questions that I want you to think about before we dive into this solution. Question number 1. What's with the restrictions on h? Why do you think that we put these restrictions that h can only be from negative 0.5 to 0.5? I want you to think about that. This is not an intuitive question. There's not an obvious answer, but I like to answer these questions by saying, well, let's play the game that these restrictions were not put on h. So let's say we could let h equal negative 1. If we let h equal -1, then this interval becomes, or this value right here becomes 0.5 minus 1, which is -0.5. And so we're talking about a time interval from 0.5 to -0.5. Time can't be negative. So we got an issue there. And let's say h were allowed to be greater than 0.5. Let's say h were allowed to be 1. Then I'd be talking about a time interval from 0.5 to 1.5. Now that doesn't seem so bad, a time interval from 0.5 to 1.5. But if we look up at our position function, t right here cannot be greater than 1. If as long as t equals 1, then the position of this ball is going to be 0, right? 16 minus 16 times 1 squared. But as soon as I go larger than 1, if t is larger than 1, then s of t now becomes negative, meaning the position is negative, or the ball is now going underground. So that's why these restrictions are placed on h. It's not an obvious answer. Second question, why can't h equal 0? Another restriction that they put on us here. So I want you to think about that. Why can't h equal 0? And again, this one's it's a little bit easier to answer than the last question, but it's not completely obvious. If h were 0, which is the way I like to answer these questions, if h were 0, then I'd be calculating an average velocity from 0.5 to 0.5. The time hasn't changed. So I can't calculate an average velocity if I'm at a single unit of time. So that's why h can't be 0. And then the third question, we can assume that t here is to be between 0 and 1 inclusively. All right, why can we make that assumption? By inclusively, I mean it can equal 0 and it can equal 1. Why are we making this assumption? And the reason is, and we pretty much just answered it, that t can't be any less than 0 because t is time. And if t is greater than 1, then this position function goes negative. So if we were to look at a graph of this, which I don't think we're going to be, but if we were to look at a graph of this position function would only make sense. The ball is falling for a period of 1 second. It's dropping for a period of 1 second, and that's it.